Okay, let's do it. The weather kind of turned on us, huh? What a bummer. It's so beautiful for a couple days. Okay, that's loud again. We've looked at a handful of ways to do motion planning now. We've done sort of the trajectory optimization family of solutions, especially the ones with nonlinear optimization. Okay, we've looked a little bit at the graphs of convex sets in the last lecture. But there's another set of algorithms that we haven't talked about yet that I think are super important to connect, to form some connective tissue in your brain here about how these other ideas you might have heard about relate to the kind of problems we've been already formulating. So you might know a lot about graph search. So you might have done Dijkstra's algorithms, A*, all these sort of traditional graph search algorithms. Clearly, we've been making analogies to doing search on a graph. So there should be some way that that kind of plays in with all the things we've been talking about. And you might have heard about the sampling-based algorithms like RRT and probabilistic roadmap. Okay, if you haven't, we'll mention those today. But the traditional treatment of the sampling-based planning like RRT and PRM are for kinematic systems. And one of the goals today is to think about how it works with dynamics like we see in underactuated, okay? So let me sort of set that up. It still seems loud. All right, so let's just think about way back when I started saying one way to do planning would be dynamic programming, right? If we were willing to sort of discretize our space, right? This was our first sort of analogy to graph search. We could just go through and tile our space with a bunch of sort of samples, call them vertices in a graph. We can make edges that respect the dynamics, approximately maybe, because it might not land in a certain amount of time exactly on the spot, but we could sort of build out a graph on a discrete approximation of our state space and do planning like that, right? So we argued that that doesn't scale, right? But I guess there's two problems with this. With sort of scaling that up to solve every problem, right? The first one is just scale. We've talked a lot about the curse of dimensionality. Right, if I just want to make a 10 by 10 by 10, let's say, discretization of my space, but if my state space starts going up, I get really big numbers of vertices very fast. There's another subtle one, which we'll come back to, it'll be important today, is that an algorithm based on this sort of a discretization loses one important property that we'd like to have in our optimizer, in our planners, which is completeness, right? It's possible that you could have a situation where, let's say there's some obstacles that I have to navigate through, okay? And maybe a path exists if I have a great trajectory planner, okay? But somehow my discretization was a little too coarse, and the discretization missed the feasibility of that path, right? So having a fixed discretization suffers completeness problems. Completeness is the definition of completeness for a planner. A planner is complete if it will find a solution if one exists, right? If I find a path from start to a goal, if the path exists, then the planner is complete if it's guaranteed to find that path, if it exists. Okay. With brute force, let's say dynamic programming, okay? Trajectory optimization, we said, gets around that, breaks the curse of dimensionality, and potentially handles some of the, it doesn't have any discretization in state like this. Right, and the fundamental way it's doing that is by examining only one solution, one initial condition, one path through space. And I argued that, that we know that this suffers from local minima. You've experienced it now, right? And you'll experience it in your project if you're using trajectory optimization, right? These suffer from local minima problems, which is a lack of completeness in the general algorithm. Okay. I sort of argued that local minima is breaking the curse of dimensionality goes hand in hand with having local minima. And so what I said is, in some sense, if you don't look at every state, then there's really no hope of knowing that you're globally optimal. Right? If I'm only examining a subset of my states, I can't know that there's some other state that I didn't look at, which could have been better. Okay, but there's an exception to that. If I can look at there's cases where I can look at a subset of the states and bring some additional information into the problem, which tells me that I don't have to look at more states, right? And in the large-scale planning literature, this is used super heavily, right? Using heuristic search. Okay, so how can we bring some of that into our space? Oh, by the way, like how does GCS approaches fit into this, right? So GCS is trying to solve the global problem, the way I've presented it so far, right? It doesn't suffer the curse of dimensionality in the same way as this, right? But it is trying to look at the entire space as presented. GCS's complexity grows with the number of vertices and the number of edges. So it's like the number of regions that you've made in your graph. It grows differently than this. It doesn't have to be exponential. It can actually be well-behaved, but it can also explode in problems where you have very complicated geometry, right? So it's got sort of different scaling laws, but it's actually closer to this, right? Trying to solve the global problem. Okay, how many people know the A-star algorithm? Yeah? Okay, I'll remind you quickly because it makes the important point here, right? So let me just give you a few of the definitions here. A-star is a form of graph search, right? And it's a case where we can get global optimality without visiting all the states. That's why I want to use it as an example here, right? So let me just define a graph with vertices V and some V, edges, let's say VI and V, edges EIJ in E, okay? I'll call the source V source, target V target. And then the extra information that you bring into A-star, which tells you there might be some, you could actually just escape from visiting a bunch of states, is this optimal heuristic, right? All right. Okay, so let me just be careful here. So let's call F the cost of the optimal path. Constrained to go through node VI, okay? And we can break that up into a cost to come from V source to VI and a cost to go, which you know a lot about from dynamic programming from VI to V target. Okay? And then the total cost is the cost of getting to node VI plus the cost to go. All right? And the way things proceed in A star is you can take candidate paths through the graph. You can evaluate their current, so I'll say a path through the graph, path P, which is just a collection of V source, VI, Vj, just a list of vertices here. Doesn't need to get to the goal. And then you can define carefully, let's say, the cost to come on a certain path, which is different than the cost to come, the optimal cost to come to get to that, right? If this is the path to get to the last node on this, but constrained to take a particular path, possibly a suboptimal path. And most important is this approximate, heuristic cost to go from the last vertex in P to V target. The cost to come is just something easily computed while you're evaluating your algorithm. The heuristic cost to go is something that you supply. That's the additional information that you supply, right? And if your heuristic has a certain properties, the most famous one being that it's an admissible heuristic, if it always underestimates, if H tilde of let me call it, P is strictly less than or equal to the actual H of the last node in P. I'll give you an example of that in a second here. So for instance, the classic example here is trying to try to do, let's say, search in Google Maps, right? I said I wanted to get to Fenway, and I'm walking, I guess. Okay, so what you want to do here is, I think a natural heuristic for anything like this would be the Euclidean distance between my start and my goal, between any point and my goal, right? Would be a heuristic of the total cost to go, right? And importantly, it's an admissible heuristic because it always underestimates. The best case would be I take a straight line from wherever I'm going there, but in fact, I'm constrained by the road networks and the Charles River, right? Okay, that's the classic example of an admissible heuristic that works for navigation. And then you might have seen this before, and I won't dwell on it, but basically by building up a data structure, which is a priority queue, where you remember which nodes you've already visited, which paths you've already visited, the path you got there, right? You insert your source to begin with. You pop out the best function as a function of my total estimated cost from the start to the target, going through that, okay? And you can just sort of work your way through this. Importantly, in the middle here, when I'm considering a particular vertex to expand, what I'm doing is I'm just looking at the successors of that possible vertex. So I'm looking at the edges of a particular vertex, right, in order to add this to the path. And I'm only inserting it if it actually makes me better. The details are less important. What matters is that if I want to solve a planning problem from my office to Fenway Park, step one is not load the entire road network of the entire United States, right? Put that in memory, formulate my optimization problem, and go, right? I'm going to start here growing incrementally out from the source and only adding edges as necessary, that guided by the heuristic to get me there. And that dramatically changes. These are called incremental search algorithms. What's important about A star and the class of algorithms like that is that they can actually guarantee that they will find the optimal path. It's complete and optimal, okay, without expanding all of the nodes in the network. So that's something we haven't had in our recipe, in our toolbox yet, right? We haven't had anything like that. Okay, if you implement this, the straight up A star, there's lots of different variants. If you implement the straight up A star, then A star actually never expands any paths with the estimated cost. The estimated total cost would be of a path P would just be the combination of those. Any path that is greater than the optimal path length, the estimated is greater than the optimal path length, will never be visited by the A star algorithm. Right? It only has to visit paths that your guess was too optimistic and could have given you a path that was shorter than the optimal path to the goal. The flip side is that it does visit every path that could be less, for which this is less than the goal. Okay, so it's extremely efficient if your admissible heuristic is accurate. If the estimated cost to go is very close to the true cost to go, then it can be extremely efficient. In the extreme, when it's the actual optimal cost to go, it'll just take the path straight to the goal. Okay. And as this bound becomes looser, then you'll visit more and more possible nodes. All right. So let's think about, that's all based on discrete search, okay? And it's a beautiful idea. And I think one of the big questions for today is how do we extend that first to continuous domains and then to dynamics, okay? All right, so let's think about collision-free motion planning as sort of the next version of the problem. So let me just, let's think about the search-based analog to this optimization I wrote last lecture, right? So there's no dynamics here. I'm just saying I want to find a series of points where the line segments are collision-free, and I'm going to just minimize the distance of those points or something, minimize the path length, right? And we wrote that last time as a nonlinear optimization, and then as a mixed integer optimization. Okay, but this doesn't have dynamics. And this is kind of the classic motion planning picture, although motion planning typically has more than one obstacle, right? This is just straight out of Howie's book on motion planning. And there's another great book if you don't know about it. Planning Algorithms by Steve Laval is still an incredible resource for this. I'd highly recommend it. It's free online. There's great stories about that. But I'll try not to get off track. Okay, so how do we take something like A star and apply it to continuous domains? And this picture sort of already gives away the basic answer. The simplest idea, you could discretize the space, but you'd lose completeness, right? And it might not be efficient in high dimensions, as I set up. The simplest idea is let's just draw a handful of samples in the space, right? We'll just start picking configurations or states at random. If we're just thinking about the configuration space version of planning, let's just say these are queues, and we haven't thought about velocities yet, okay? I'll just pick them at random, uniform random number generator. If they land inside the region, I'll reject that, throw that out. If they land outside the region, then I'll add this to my roadmap, okay? And then I'll immediately look in the roadmap for other nodes that are close to that node. And if I can connect them with a straight line that is collision-free, which is often, if you only have black box access to a collision engine, that means actually making a sample-based approximation, sample, 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 to make sure all of those points are collision-free. Okay. Then I can build up this sort of roadmap a priori, right, with a really simple, I'm going to pick a random configuration, check if it's collision-free, insert it into that roadmap. And then for all of the nodes, in the general case, for all of the nodes in the roadmap, I'll check for the nearest neighbors, check if that path is collision-free, and add that edge. Okay, and then at the end, you can do A star, right? So now if I have a new motion planning problem, I already have a roadmap that's sort of worked out my space. Then if I have a new initial condition, probably, with probability 1, it's not on the existing roadmap, but I can just I can do one step of the algorithm to connect me up to the roadmap, right? Draw an edge to that. And similarly on the goal, I'll take one step, I'll just find the closest point, connect it in, and then do A star on the existing roadmap. Yeah?
I feel like the shortest path would be something that would sort of wrap the obstacle very nicely.
Excellent question. So if you know your objective is shortest path, then you would expect the vertices of these obstacles would be like sort of the key elements, and you should definitely sort of put sample points there. I think that's absolutely true. People, in 2D examples, we actually can crush these problems. We can make Voronoi decompositions, we can solve these things to optimality, and even in polynomial time in 2D and stuff like this. So the 2D is visually appealing, but too simple, right? So the question is, how do you do the same thing in like configuration space of a humanoid? And then finding corners of configuration space obstacles really isn't viable. But you're absolutely right. In this case, if I'm solving minimum time problems on this problem, I should put my sample points at all the vertices. Maybe not that one, but yeah. Yes? Awesome question. So yeah, would you want to execute this trajectory? I mean, certainly, like this kind of thing is really bad. So there's two aspects to that. So one is that I think we haven't got dynamics in here yet. So if you had velocity limits or torque limits or something like this, if you just tried to execute this as fast as possible, given your torque limits, you might be extremely inefficient. You might have to like almost come to stop and start again. So that's a problem. And then the second one is, it's just like non-smooth, and like, why would you want to be dancing around? Although, yeah, so that's the main theme of the lecture, is how do we extend this to state space? Yep, for sure. People do filter these things before they execute. Having said that, it is not hard to find online a video of a robot executing in these kind of planners and looking ridiculous, right? You can look at like companies, front page of their website, and the robot's going, it just wanted to move from here to here, and it kind of went like this, and it happens. Yeah, some of the best planners we have do that.
I guess maybe it's the next step, but I guess for the dynamics, you kind of like carve up the areas for which
That's one. We'll talk about exactly that. I think you're thinking about the right things. Yes. Okay, so let me just let's just think about the properties of this. So, is this a complete planner? Oh, sorry, I didn't see.
What's the
Yeah, let's see. So you can implicitly compute the Voronoi regions. You probably wouldn't want to actually write their faces and stuff like this, but you could have the implicit representation of the Voronoi. But that's just the nearest neighbor queries. The first answer to that is that the actual obstacles, if you take a three-dimensional obstacle and then look at it in joint space, then they're not convex obstacles, and they're not even polyhedral obstacles. You could have a polyhedron in Cartesian space, and they look terrible and curved and everything like this. So you would need to somehow take the Voronoi regions of the sampled points along the surface of this boundary in high dimensions, and I think that's where it starts breaking down. Yeah. 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 Okay. So that's really good. So there are ways to make sparser versions of this. I think both. I mean, you'll see in the literature, you'll see cell decomposition methods that try to come up with like the minimal sort of covers of these kind of algorithms, and they typically work extremely well in 2 and 3D and start dying afterwards. You can do. There's also ways to make sort of sparse versions of this, where you it's a bit like doing a triangulation in the middle. There are visibility PRMs and other ideas like that sort of connect the randomness that people like about this with the triangulation ideas that you're talking about there. So definitely there's things like that out there. Yes?
When you apply the dynamics to this path, you have to now do another nonlinear optimization to cover for the obstacles?
You guys are...
So the dynamics could run into it, or another mixed integer problem?
Good. Okay, so let me get to that. So let's just... what are the problems that make that? Let's just do a thought experiment. Like, let's say I have the pendulum dynamics, right? Would PRM solve the pendulum? So this is theta versus theta dot. Does PRM solve the pendulum? Okay, so the first point, I think, which you're kind of getting at here, both of you are getting at, is that, let's say I pick a point at random, great. Now I pick another point at random. So it's perfectly reasonable to draw an arrow like this, right, in this case, because this is dynamically feasible. It's not reasonable to go the other direction, right? So suddenly we must go from an undirected graph to a directed graph. That doesn't seem too terrible. But there's another problem too, right, which is that the notion of distance is kind of broken, right? So let's say I have a point here and a point here, right? If you ask what's the sort of closest point that I should try to connect to, right, it would naturally say that this is a close point, but actually the path that would take to get from here to here, if I did call a nonlinear optimization, might have to go all the way around in order to get back, right? Maybe even more dramatic if it was right there, right? Okay, so these are the things that are going to make us have to rethink some of the basics when we get to state space. You can try to do this. If you do have a point that is reachable, you could try to make that connection with a nonlinear trajectory optimization or mixed integer optimization. But oftentimes we can get away with nonlinear and just rely on, with probability 1, eventually we will sample close enough that the nonlinear optimization will be successful. Okay, something like that, kind of those kind of arguments. So, okay, yeah. So is this algorithm complete? It's complete in an important, certain special, variant, right? It's probabilistically complete. So if I sample enough points, as the number of samples goes to infinity, then eventually I get completeness. Yeah. I think those are different ideas. Unless I'm not connecting something, but yeah. Yeah. I see. Yeah, okay, in the sampling sense. This is a slightly different idea still, I think, yeah. But good. So if you sample densely enough, as the number of samples goes to infinity, then the system is complete. So people call that probabilistic completeness as a property of the algorithm. It's actually a pretty weak property of the algorithm. Like you can basically use a random number generator and call that a probabilistically complete planner. So like with I'm going to just randomly pick any trajectory, and as the number of samples goes to infinity, I'll eventually accidentally hit the goal, right? So that's a probabilistically complete planner, not one I would recommend, but it sort of works, okay? And then is this optimal, right? Again, in the limit, you could argue that if you're using an optimal graph search, in the limit, it could be probabilistically optimal. You have to be a little careful making that argument. There's extra work on asymptotically optimal versions of this planner. which you get PRM star as a variant of the algorithm, okay, which try to carefully maintain the graph such that as you keep adding things, you rewire in order to make sure that the shortest paths exist with probability 1 as the number of samples go. Okay. So there's a couple problems of making it go to state space. The other thing that I think you kind of all pointed out, which I kind of want to emphasize here, is that these straight line segments, if you do have dynamics, right? If this was a state space, then you can't just take arbitrary straight line segments, right? And to some extent, if you've done your pre-computation thinking about only these straight line segments, then in my mind, you haven't left any room at the end to examine, let's say, smooth curves or something like that, right? So I think the sample-based, looking only narrowly at sample points is kind of a narrow way to pre-compute your space. Cool. Okay, so here's like the, maybe the GCS version of that, okay? Imagine every time you pick a sample point, you try to grow a region instead of just using that sample, okay? And then you could still try to probabilistically cover the space now, but actually with a finite set of samples, you could completely cover a space, right? And more importantly, you could leave room, you can parameterize continuous curves inside each region and then have enough room left to do optimization in order to satisfy dynamic constraints, okay? So that's one idea along this line. Since a bunch of you are playing with Iris, I heard a conversation about that just as we were going. I've been putting together as many notebooks as I can to help out. So let me just do it there. This is one of our simple examples that we used in the paper. I just tried to carve it over, and this is actually just the manually designed regions first. And this is what GCS does, finding straight line segments if you're just doing piecewise polynomial or piecewise straight segments in that problem, okay? And if you start adding more constraints, this is the one that I told you about that has acceleration and jerk and other limits, then you can get these beautiful solutions. That's the version that is still in code review and should be available in Drake soon, yeah.
Did you run Iris on that 2D plot?
So let me show you that.
Are you intentionally choosing your centers to get inside those little corridors?
So what I did for this, so here's an example of how we can try to come up with it. So this thing here, this picture at the bottom, is a cover that was obtained by the sampling algorithm, right? And let me tell you that idea in just 2 steps. I know you have already talked to Pete about it. This is Pete's algorithm, actually. TA Pete made a version of this algorithm. Actually, I have a slide about it. I think it's better on the slide. Okay, so first of all, you guys, a bunch of you are using Iris, so I forget that I haven't actually said it in lecture yet. What the heck is Iris? Okay, so Iris is the way that we generate big regions. Okay, it's a simple little iterative procedure that solves some optimization problems that try to find big polytopes and then ellipses that fill up the polytopes. And if you have a bunch of obstacles in a sample point, it will find a big configuration-free, a collision-free region in configuration space. Okay. You can think of it as the configuration space you want to do a convex decomposition of this collision-free space. And this is one step of that algorithm where given a point, you try to find a big region. And then we have more complicated versions, newer versions that try to do that even in the configuration space, where now the boundaries of even simple geometries get complicated when you multiply them by sines and cosines and lift them into high dimensions and things like that. Okay, but we still look for polytopes traditionally that do convex decompositions of configuration space. That's when you hear about Iris. That's what we're talking about, is that class of algorithms, yes?
So this is from 2014. So I'm trying to understand, why is this even outside
So the original genesis of that algorithm was for footstep planning on the humanoids during the DARPA challenge. And we didn't have GCS yet, but we were able to write mixed integer planners that could plan, tens of steps in reasonable amounts of time. Now we can, solve arbitrarily long sequences because like the relaxation is tight and we can just solve an LP like on your problem set. So it's just gotten better, but it was still useful back then. Even doing quad rotors and stuff was possible then, but it was much more expensive. Okay, and these regions, even these configuration space regions, a lot of people are afraid of those regions. You should be a little bit afraid of those regions, okay? But they are actually amazingly good. Some of the simple geometry algorithms do really complicated things. So like this was just one thing that we wanted a sanity check about is like, can we actually reach in to a shelf and pick up a mug if we're just computing these regions that are supposed to be the big areas of configuration-free space? This is like a region, this is a 7-dimensional, 7-degree of freedom robot arm. So the way I visualized it, because it's hard to visualize things in 7 dimensions, is I just taking a random walk in the polytope, okay? And it gets right up to and around the obstacle, right? So it's not convex in the Cartesian space, it's convex in the configuration space, and it's collision-free, but it gets right up and into the problems of interest. Okay, to the question. So this is Pete's work. If you want to now cover the space with iris regions, back in 2014, we did something more naive where we just sampled at random, we grew a region, then sampled again. If it's outside the region, we would add something. But that makes pretty inefficient covers. It works, but it's inefficient, right? And you can do better by, you start with a bunch of samples, and you build something like a probabilistic roadmap. It's called a visibility graph. The only difference is that in the probabilistic roadmap, you only try to connect within some small epsilon ball. And in this one, we're going to connect no matter how far away. We're going to consider every possible neighbor. And if anybody has a straight line, then we'll say it's visible. Those two nodes are visible, so we're going to add an edge. Okay. Now you have this discrete object in the space. How does that help you find a convex decomposition? Well, if you think about it, there's a graph concept called a clique. Okay? A clique in the graph is a set of vertices that are all connected with each other. This is a standard concept from graph theory, is if you have a bunch of vertices where all of the vertices are pairwise connected, we call that a clique in the graph. You can try to find maximal cliques, right? And it turns out a clique in a visibility graph has a nice correspondence, not a perfect correspondence, because there could be an obstacle you missed in the middle or whatever, but this corresponds to potentially a collision-free convex region in the original space. It's like the discrete analog of finding a convex region. But then to finish the work, we take that as an initial guess and we call the iris algorithm to blow it out. And this has a bunch of advantages over the original. Partly it's more parallelizable, but it also gives more efficient covers of the space. This is active work. Pete's got a new version that's going to be even better, which makes GCS perform a bit better, because one of the things that happens with the current versions of the algorithm is it kind of minimizes the number of vertices, but GCS's performance scales more with the number of edges. That's the number of costs and constraints that get added to the problem. So you really want a slightly different version of this that minimizes the number of edges in the graph. And some of these get really big connectivity and can be slow for GCS. But it's super satisfying to solve geometry problems that are fairly classical, have some new approaches to them, and have it get all the way through to making robots move better. Yeah, so that code, an example of that code is sitting here. So I just, for this region, this set of obstacles, you can just call the clique cover, and it just calls iris a bunch of times and generates that. Okay, and you can mess around with that if you like. It's also interesting, since you guys are asking the good questions and everything, so let's just think about this one for a second here. So the difference between the straight line segment version and this version is that it has velocity limits, acceleration limits, It also has continuity constraints between the segments, right, of up to high degree to make sure it's a smooth trajectory. It turns out if you have only continuity constraints up to high degree, but you don't put velocity or acceleration limits, like what it's really, this happens sometimes in RL too, but once you have like a stronger optimizer, it will make you realize that your cost function, you have to make sure you wrote the right cost function, because otherwise it'll give you an optimal solution that you didn't want, right? So if you were to say, I have a polynomial of degree 10, okay, and I'm going to say that the segments have to be differentiable to arbitrary degree, so let's say degree 6, okay, then Jagdeep's problem is actually still true. Like what it will do, for instance, if you're trying to move around these obstacles, right? If the piecewise linear optimal solution was something like this, okay, and I wanted something like, this, because of constraints, if I only said you have 10 degrees of polynomial to play with, and you need to be, smooth here, continuous in derivatives up to whatever degree, then what it will do is it will put all of the points right here, and it'll come up with like a super, smooth, technically smooth, but arbitrarily tight approximation of that line, right? That is the optimal solution. And so it's almost indistinguishable, meaningfully indistinguishable from the straight line version. Okay, and so the original quadrotor paper, the original GCS paper that had quadrotors, I said I wasn't completely happy with the quadrotor solution in that. That's because it was doing this, and all we did was we put a heuristic in to try to spread out those points so they couldn't bunch up too much. And the new version here, where we're putting in nonlinear constraints in the rounding step, can now give you these beautiful solutions. Cool. Okay, so I mean, GCS is kind of one way to put dynamics into the PRM. But the more famous way is to do a slight tweak on the algorithm. And the more kinodynamic version of this was originally, that was one of the motivations for the RRT. So let me tell you what an RRT is here. Rapidly exploring random trees. Okay. So the motivation, I think, behind RRT, this was came out in 2002. James Kuffner and Steve Lavelle introduced it. Super elegant idea. Super popular because it's very easy to implement and very effective. I suspect they were thinking about trying to put A star back into PRMs or something, right? So the problem with PRM is that you still have to sort of cover the entire space in the roadmap creation step. The A star is making the graph search part effective, but the discretization doesn't think about the source and the target. You're still having to think about the entire space. How can you leverage the A star idea and try to guide the search to cover less of state space and scale to bigger problems? Okay, and the algorithm that came out of that is actually extremely simple. It looks like this. Okay, let's do it. It's a recursive algorithm. The first step, we just have one vertex. Let's say it's at the source, okay, or Q init. What we're going to do is we're going to sample a random point. We're going to build this tree, this random tree. At every step of the algorithm, we're going to sample a random point, call that QRand. We're going to find the closest point in the current tree, call that this Q near, okay? And then we're going to extend the tree in the direction from this point in the direction of QRand, not all the way there necessarily, typically not, okay? And then we'll add this, as long as it was collision free, we'll add this to the node, to the tree. Okay, super simple algorithm, like deceptively simple. A lot of things that look like this don't work at all, okay? But this works incredibly well, okay? So let's just think about what that's doing. Okay, this is like an example of a classic motion planning problem where you start, it's called the bug trap, right? You start inside the bug trap and you have to find your path to the goal, okay? And this algorithm will grow out this rapidly exploring tree, okay? It'll fill up the inside, but it will keep going. If you keep drawing samples, it will eventually, with probability 1, find its way through the narrow corridor and get all the way to the goal. It's like one of the incredible things about RRT. People talk about, oh, narrow passages are a limitation of RRT. The flip side is that it actually does still work. It's just inefficient potentially if they're too narrow, but this is an incredibly powerful version of the algorithm. Yeah. It's like fractal art. It's better than that. You'll see that it's that the fractalness of it, if you will, is actually an essential part of the algorithm. Okay, so if you just do it in an open space, it does this. Okay, this is my Meshcat version of it, so I can. Let me do it maybe a little slower here. So what it does is it starts by growing out very quickly all over space, okay? And then as it proceeds, it gets denser and denser and more fractal. It's one of the most important parts of the algorithm, okay? Properties of the algorithm. Okay, and that's what gives you these bug trap kind of solutions. All right, so let me step through that. So here's an almost identical algorithm that sounds similar, okay? Which is I'm gonna take my current tree. I'll take a random node in my tree, and I'll just extend it into a random direction, right? That's kind of, it feels similar. Like I just want a random tree, so I'll pick a node in my tree, and I'll grow it out in a random direction. That doesn't work at all. That gives you hairballs, right? Because basically it's doing a random walk around the origin, right? And it doesn't have any incentive to do this sort of exploration first and then fill in the details. Yeah? It could be. Yeah. I mean, it's, yeah, there's a lot of, Brownian motion is everywhere, I think. Okay. Here's what the RRT is doing with maybe a Voronoi regions drawn on top. Okay, this is one way to think about how they have the property that they have. They have something called a Voronoi bias. So obviously a few of you have already asked about Voronoi regions, but let me just make sure people know what a Voronoi region is. So if I have a bunch of points in space, then the Voronoi partition of this space is if I make a region that contains all of the points that are closest to each point, okay? So basically the way I would draw this is I'll take between every 2 points, I'll draw the line that's exactly splitting those two in Euclidean distance. So I have to do it here, okay? I have to do it here, I have to do it here, right? I should have made it easier for myself, but it's kind of a hard one. Okay, something like that, and then what happens in the middle here, it goes like this, and I don't know. Yeah, that was really hard. Okay, something like that, right? A little detail missing in the middle. Okay. Right, so this region here is the set of all points that are closer in Euclidean distance to that point than any other point. Right, and so I can find them by basically, in a simpler example, right? If I want to partition this space, the straight line between them, this is going to be this one's closer to this is going to be closer to this. Okay, why do I say that the RRT has a Voronoi bias? If you think about the algorithm, I'm going to draw a sample at random. The probability of drawing a sample and choosing the closest point to be this point is proportional to the volume of the Voronoi region. Okay, so basically the size of the Voronoi regions tell me the probability of extending that from that node. And what happens is initially, the points on the boundary here have a big Voronoi region. So with high probability, they get expanded. Okay, and then after it sort of covers the space, then the size of the Voronoi regions is more uniform, and it starts picking off the Voronoi regions on the inside and growing into them. Right? So it's like a 3-line algorithm, super simple, that has this incredible property of growing everywhere rapidly and then filling in the details to look for nooks and crannies later. Yeah? Good. The simplest version of RRT is just you pick a point at random, you literally use the Euclidean distance, and you grow some, you typically have a maximum distance that you're going to grow towards that. So you either grow all the way to it if it's less than that distance, or you truncate in the direction there. And you only add, of course, you're always doing collision checks to make that work. When you have a goal, then you typically will, with probability 0.1, sample the goal. And then with probability 0.9, sample an arbitrary point so that you're goal directed. And that's where you get some of the A-star behavior back, is because the distance is your admissible heuristic that's dragging you towards the goal, probabilistically at least. Okay, so this is an amazing algorithm, super simple. It works for pretty complicated systems, right? So even back in 2002, 2003, 2004, James Kuffner was the one applying it to humanoids, right? So James went to Japan and worked on this series, that's H7, one of the early humanoids. It's crazy that there's a new humanoid like every week, or two this week, but at least two this week. Okay, but the fact that you could do an RRT on the full space, the full joint space of that robot in 2003 or whatever was pretty awesome. Okay, and actually that trajectory is dynamically feasible. So how did he do that? Okay, so you choose a configuration space trajectory Q, okay, that goes down and reaches down, and then when he's going through and to put in velocities and accelerations at which he traverses that path, he uses the ZMP to filter and choose. He will never choose an acceleration that will move the center of pressure outside the support polygon. So these were using ZMP to do planning in full dimensional humanoids. And they can also solve like awesome geometric puzzles, right? So this is 2001 C actually, right? So all these geometry puzzles, right, that you and I have trouble solving, maybe just me, right? But RRT can just nail those. Yeah. Okay, there's subtle ways, subtle pieces of that version. So in general, if you have a goal region, that's fine. You can just pull some sample out of that region. As long you need the ability to sample from the goal set, right? In configuration space, if you're saying, so typically you would actually make a configuration space goal. If you had an end effector goal that was specified in configuration space, then you could, the inverse sampler is hard. You can call it inverse kinematics or something like that to do it. But there are a lot of cases that are easy. And I think typically you want to think about that as through the forward version of the problem. So I'll sample in Q, figure out if I'm in the goal or not on the other side. Mm-hmm. Okay, thought experiment. Does the RRT work for the pendulum? Right? If you just take the straight up RRT algorithm, maybe with one modification, is when I go to connect, I will use torque basically to connect, right? So I'm going to pick a point at random. I'm going to find the closest point with Euclidean distance, and then I will just take the U, which gets me as close as possible to that point. Okay? And not only does that work, but of course it sort of figures out the eyeball, right? It has to in order to get to the top. So right out of the box, the RRT, in fact, it was sort of motivated initially by being a kinodynamic possible planner. That's the name of it. We distinguish between kinematic motion planning versus kinodynamic. In the sampling-based literature, this means under actuated robotics. So this one means manipulation, something like that, right? Yes?
How do you pick the initial node in that case? Is it just the origin?
I picked the origin and picked the goal as the upright. And I sampled with, I did the wraparound so that that is 1 point, even though I drew it twice in the plot. Okay, so RRT can solve dynamic problems, but it's not good. It's not good at it. People can basically consider it very ineffective for solving these problems. It takes lots and lots of samples. And if you start working on this, you will quickly understand it's kind of maddening, okay? Because it's still using the Euclidean metric. So what it does is you see like the density of the samples that it's exploring here. This looks nothing like that beautiful Voronoi exploration that we saw before, right? So basically, every time I draw a sample here, in the Voronoi case, if I draw a sample here, I'm going to grow towards it. And drawing a sample there again will now go to the new point. It won't keep expanding the original point. If I draw a sample here now, and I extend this, I draw the sample again, I'm going to extend this again, right? The fact that the distance metric is poor for the dynamical system makes incredibly inefficient extensions to the tree. Right? If I just draw that, we've lost the Voronoi bias, okay, and we're in practice getting very dense trees. When you get very dense trees, then when you pick a point at random, you've got a lot of things to compare against. So even the nearest neighbor queries gets more expensive. Okay, and in general, it becomes a very inefficient way to grow a tree. Yeah.
So then is this a problem with the algorithm or a problem with the metric? Like presumably you have a metric that considers the controllability or needs to be, I don't know about randomization.
That's exactly right. So the question is it a problem with the algorithm or is it a problem with the metric? So what I basically want to say is that there were 3 steps of the algorithm. One is that you pick a random point, and the naive sampling distribution is actually, you can make that better. You can make a more dynamically aware sampling distribution. The second step is finding the closest point. You can find a more dynamically aware version of the nearest neighbors, a better distance metric. And the third one is that you do an extend operation, and you could do trajectory optimization or something better to do extend operations. That's roughly what I want to say in the last part of the lecture. So all 3 of those, the 3 basic steps can all be made more dynamically aware, and you will get better RRT performance if you do. Other questions on that level? I saw some other hand, I thought. Yeah?
RRT uses Euclidean distance to find the next point, or the nearest point.
Yeah, you can insert your own distance metric, but that's the most common one, yeah.
Okay, so like for just a dynamical system, cosine or
What should you, that is a good question. What should you use? Let's talk about it. We can do the distance metrics first. That's great. All right, so let me just write down what I just said here. So there's 3 steps, 3 core steps of the RRT. One is the random sample. Right, so maybe we want to find a better distance. Second one is find the closest point. I call it closest vertex, just to be clear. Vertex on the tree. Maybe better distance metric. And the third one is better extend operation, or doing the extend operation. And then we can do calling full-on nonlinear trajectory optimization at every extend gets a little expensive, so people don't often do that, but that's, I think, a reasonable mental model to have of how you could try to do better. Okay, so you guys are keying in on the distance metric. So what's the right distance metric? If I've got this picture in our head of, I've got 2 points in state space. Some of them are very, this one's close, this one's far, even though it's close in Euclidean metric. So you said use some sines and cosines. Is there a general principle of like what I could think about if I wanted the distance between 2 points? Let's say even a one-directional distance, because I think this makes it clear that, I mean, a true distance metric, okay, a metric is going to be symmetric. So it'd be, for any 2 points, the distance from A to B should also equal the distance from B to A. That we're not going to have that. We're going to throw that out. Let's just do a one-sided distance metric. So I just want the distance from A to B. What's a good way to sort of compute that distance? Yeah.
The Jacobian?
Okay. So you could do some sort of a linearization of the dynamics here and talk about, I mean, we still have state and control. So Jacobian isn't going to tell me anything about U, if you will, right, the inputs. So maybe that's part of the answer. But linearization is totally reasonable.
Yeah, just solve the dynamics. It's feasible and then feasibly connect.
Okay, so that would be like if you say, but I want to know who to connect from, right? It's not enough. There's in the extend operation, then that's you just try to solve the dynamics and then connect if you can. But first, I'm trying to decide where I should connect from. So I need a scalar quantity that's the distance to all the points. Okay, yeah. So like the magnitude of the control input, I think that's exactly right. Maybe the generalization of that would be whatever your cost function is, I think this should be the cost to go. Right? So what you really want is, given a point, you'd like to instantly compute the cost to go of all the points from here for whatever cost function you want. And your proposal was a cost only on U, which is perfectly reasonable, right? But maybe you have time as a cost, maybe you have other things as a cost, right? So I think the true distance to this point is a dynamic distance is a cost to go function, right? Which, I've drawn them for the pendulum. They can look beautiful and swirly and multicolored, right? All right, so I think that's a key idea here is let's think about the cost to go to X, or let's say Q in these problems. Well, I'll say X because we're in state space now. X random. And if you could evaluate the cost to go, for instance, if you could just compute, do value iteration on your problem instantaneously, right? And then you could very quickly evaluate the value on all the different nodes, and you can pick the closest one. That seems intractable to do, okay? You don't want to do that in the inner loop of a randomized algorithm that's going to take 10,000 steps, right? But that conceptually seems very nice. So let me see, I think I've gone out of order now, but that's actually pretty good. Okay, so here's one I really like. So Emilio Frizzoli was a faculty in Aeroastro here. Now he's at ETH. He left us, sadly. But this is his thesis back in the day, which was awesome. Okay, so he was picking up right around the time when the RRT and everything was coming out. He was kind of, from a controls perspective, thinking about how those algorithms could work. And he proposed using a cost to go to guide the search. Okay, and in particular, he thought about helicopters and other agile vehicles flying around obstacles. Okay, so the key insight there was that if you have a helicopter dynamics, okay, it's let's say 6 or 7 state variables if you use quaternions, okay, positions plus another bunch for velocities, so you're like 12 or 13 depending on how you parameterize it. Too big for value iteration. Okay, but if you start realizing that there's some invariance, right? So or equivariance in the dynamics, right? So the horizontal position of the quadrotor or the helicopter doesn't affect the dynamics, so I can ignore that. There's other sort of the role invariance, things like this. So you start chopping it down, and he got to the point where his state space was, for the unconstrained problem, was sort of tractable. So you could just say, given a point, I'm going to compute an approximate value iteration solution that tells me from all the other points, if there's no obstacles, how do I get to that point? And he did that once offline, and it probably took a while. Okay? But then he had this function, and what he did was he used the cost to go of the unconstrained problem as the heuristic search. The cost is the approximate cost to go for the constrained problem. Right? So now you put obstacles in there. The true distance is higher than the unconstrained problem, but the cost to go of the unconstrained problem is still strong enough to guide the search. That make sense? Okay, so everything you've learned, I always try to find ways to say that the things we've learned all semester are very important, right? Everything you've learned now about solving cost-to-go functions makes you better at planning, or sample-based planning. You can bring that to bear. So, moreover, he had sort of a philosophy in that work, and I think it continued throughout his work, of using control sort of in the loop. So you shouldn't, he didn't like, I hope I'm not putting words in his mouth, he didn't like sort of incremental small updates that are just choosing U at random. He would always put a low-level controller in and think about these as trims and maneuvers that would connect points that were potentially far away, okay? And you always want to do your RRT on a closed loop system that is stable, he would say, okay? And so he had these trajectories that looked sparse and beautiful, but could find their path to the target, guided by the cost to go of the unconstrained problem. Okay, so that was really good for the helicopter stuff he did. In particular, if he was willing to do that one-time value iteration sort of numerical exercise, okay? If you want a more general purpose one, then I think you do get into the limits of what value iteration can do, right? So another idea, like a linearization-based idea, is you could take a point in your state space, you could linearize the dynamics, make a AX plus BU approximation of this, and solve an LQR problem, right? And try to have an LQR cost to go that tries to approximately guide your search in with a cost to go. So there's a class of algorithms that have used LQR as a cost to go heuristic to guide the search. You can't take, LQR doesn't have a solution around a velocity that's non-zero, right? We've always done LQR around fixed points, or you've done, or we did sort of time varying minimum time problems, other things around non-fixed points. It's fine, I don't need it yet. Okay. So you can there's kind of a hacky version where you just pretend it's time invariant and do your best, or you can try to do the more expensive LQR, thinking about stabilizing, getting to, at some fixed amount of time, a velocity that's non-zero, right? But that's sort of those are two maybe ideas along the line of trying to do a better distance metric, okay? And in general, I think anything you can do to do approximate cost to go can help. There's a large literature now on learning to plan, right? So you can imagine doing you could do reinforcement learning, you could do a variety of different learning algorithms to try to do approximate versions of this, and trying to learn sort of distance metrics or sampling heuristics, things like that. Okay, let's think about the sampling distribution one, okay? Let's say I take my pendulum example. Okay, so I've got an RRT that's sort of growing out. I've got a partial tree here, okay? Got all these different. This would be a dream if it were to open up just this well, but okay, something like this. I've got an initial tree, And now the naive sampler would be pick a point at random at uniform, okay? But there's a bunch of states that, like, if I sample over here, I'm not getting there anytime soon, right? If I sample over here, there's really no, I'm kind of wasting effort sampling over here. Where I really want to sample from is kind of like on the fringe of what my current tree is able to do, right? That's where I could sort of hope of reasonably guiding with a short-sighted planning algorithm to do better, okay? So this is where someone said, Mike said about the reachability, right? So imagine I could somehow magically compute the reachability regions of every point that I've got in my tree. If you could just sort of say, this is the set of regions that I can get to in less than delta t seconds. This would be, like we talked about, you could use sums of squares for this, but probably not in the loop, right? This would be like the reachable set. The 0, or let's say the dt, or 1 time step reachable set. And really, I'd like to compute this for every point. I mean, it's just in 2D, it's just looks like this, right? In fact, if it's a discrete time system, it's actually just it looks like this, right? It's going to be something like this, for instance, okay? So there's been other lines of work that have tried to do reachability-guided sampling-based planning. See if I can get the projector back. All right. Okay, here's an example of sort of a reachability-guided RRT. If you can come up with a heuristic for sort of gently, approximately estimating the reachable set from each of those points, then you can imagine, and in practice, this one's like was still going, right? This one got to the goal very quickly with a much, much, much sparser tree. The only thing changed between those two was that instead of drawing samples uniformly over the space, it only draws sample at the fringe of the tree. Okay, actually what it does is it draws sample uniformly across the space and then rejection samples to see if you're in anybody's reachable set. So basically you sample, if you're over here, you reject. If you're in somebody's reachable set, you keep it and you extend, okay? Again, that was actually just using linearization around a point. You do the linearization and you do an approximate reachability computation. Okay, and it has this nice interpretation that the Voronoi bias, right, is kind of at work. So you can say the chance of me. So this was actually I forgot. This was a simpler version of that. So there was no reachability computation in this particular version. It did something more clever in a sense, but limited to simpler problems. But one way to do this was as soon as you add a node to the tree, you also just say project like what is u max and u min and see where those get, okay? And if you have n actuators, you have 2 to the n of those to project, or you pick some subset of that, okay? And then what that particular algorithm did is it picks a point at random. If you're closer to the sort of extreme points that have been raised than you are to any of the other nodes, then you must be in sort of the reachable set of that algorithm. It was just an efficient approximation to saying that if you're close to the nodes that are reachable from this, then you should probably try to grow that node. So the Voronoi regions here had this sort of nice look where they was trying to pull on the edges of the reachable set. I think more generally, though, you'd want to do some sort of basic reachability computation. That's back in the day. That's what was the first way we made our little dog bound over rough terrain with these sort of reachable sets. All right, maybe I'll just say, since I'm about out of time here. Oh yeah, this is the newer version of it, actually. I guess Terry and Peng have a new heuristic for doing reachable set computations for contact problems that are quasi-static. Works really well. And now they've got sort of sample-based planning algorithms that can solve some of the harder contact problems, including dexterous hands, things that, like, I guess 2 years ago, you would only associate those with RL being able to do that. But RL would take a lot of resources to do this. And when you can get these sample-based planners to work, they can work in seconds on a CPU. It is written in Drake. The full algorithm is, I think, open source, and uses Drake, but the actual algorithm is not in Drake yet. Yeah, Terry's got this working on hardware now too. It's pretty awesome. Yes?
So I said order of 1 minute. Order of 1 minute. It took on the order of 1 minute to calculate all of those plans. On what?
On a laptop or something. It was. Yeah. Yeah. It's true. It's a good question to ask because every once in a while it's like on a 64 GPU farm in the cloud. It wasn't that at all. Yeah. Good. All right, let me just maybe say one thing at the end here about using trajectory optimization to extend. Okay, since you guys are aficionados in trajectory optimization, I think there are a few things that you can do that make this really work well. Okay. So imagine I have a set of trajectories like Emilio's examples, for instance, okay, that I'm trying to grow. I pick a random sample. Okay. Now, the simple thing to do would be to find the closest point with whatever distance metric, the best distance metric you can bring to the table, okay, and then start doing trajectory optimization with this as an initial condition and this as a final condition. Okay, and that will work, but only when this point is reachable from there. But you guys know the flexibility of trajectory optimization. So one thing that we did back in the day that makes it a lot more effective is rather than treat this as an initial condition, we said this is your initial guess, but the initial condition is just constrained to land anywhere on this tree. Okay? So for instance, the optimizer, even though it's maybe initialized with a straight line like this, could find a solution that connected from there. In fact, even if you write the distance to the tree sort of equals 0 as constraint, it could even, during the optimization, it could snap over and come from there. And you could lean a little bit more heavily on the nonlinear trajectory optimization to get connectivity during the extend operation much more often and get much sparser trees. Okay? So people have done a lot of work on nonlinear trajectory optimization plus, used in a sort of RRT framework, and that can be very powerful, actually. Yeah.
Is there not a way to use like LP to solve that?
So if the dynamics are linear, or if you're just in configuration space, then you can write simpler things. But I think if it's the nonlinear dynamics that would typically make it a nonlinear optimization, right? Or the constraint. I mean, it depends how you parameterize your trajectory. If it's a piecewise polynomial, you'd have to be clever to write that as a convex optimization.
So there are variants where you just, like, if your distance is very close in like the visual space, you just linearize and do it?
Yep, I think all those things are possible. So I think you could lean more on the sampler, or you could lean more on the trajectory optimizer. The slight preference I have towards leaning on the trajectory optimizer is because if you lean on the sampler, you will pay a price later because you'll have a dense tree. Right? If you can keep your tree sparse, then all of your nearest neighbors queries are faster. You do less optimizations. So it's actually, it often behooves you to keep the tree a little sparse. Unless you're on a 64 GPU cloud machine and you don't care about that stuff. I would just add a new, because this was also a reachable point, right? You could get from here to here, so that's viable, right? But then you only add if the trajectory optimization is successful, and you add it from wherever it was successful. This is still, I mean, there might be other points here that you would want to go from there, right? So I think any solution that you found is a good one, potentially, is maybe my, of course, there's every example. You can come up with an example where you would want to do that, but I think in general. Okay, that was a quick version of sample-based planning for dynamics. All right, see you next time.